Hello everyone again and welcome to my channel. So in here we're going to be looking at the intermolecular Diels-Alder reaction, and Diels-Alder, of course, you're looking at cycloaddition. Specifically you will be looking at the 4+2 cycloaddition, where the 4 is coming from this particular species over here and the 2 is coming from this particular species over here. One thing we have to note here is that there will be some changes in the molecular orbital in terms of the coefficients, where some of the lobes will be bigger than the other, and that will be critical in terms of the positioning of the molecules as they are arranging to form our final product. Note also here that there will be a change in the stereochemistry over here, where you see these two particular substituents being positioned C's to each other. Quite exciting that we're going to get a C's product, and thereby what we need to do is that we need to position these two reagents in such a way that they will be C's with each other, one at the top and the other at the bottom, and then that will enable us to actually get our product. Now before that, let's look at this particular reagent and let's see which particular possible molecular orbital combination will be necessary for we to be able to make this to be our HOMO. Now in here, if you look at all the possible ways, we have 4 carbon atoms forming this nice conjugation over here, and what happens here is that there are 4 possible ways. We have 1, 2, 3, 4. Now first is this, where all of them are in phase or shaded with each other, and then the next one is just one node at the center, which is actually over here, and then these ones here, first 2 are in phase and the other 2 are out of phase. Now the third one, we have 2 nodes and 2 nodal planes, pretty much try as much as possible to be symmetrical. Oops, but anyways, I'll just make this shaded as well, but this is different from that. Make this shaded for now, then I'll include this particular point over here, and what happens then is that these 2 over here are all in phase but out of phase with respect to this particular combination. And our last one over here, we have our nodes, of which all of them are actually out of phase with each other. So out of phase, and out of phase. Now what happens here is that if you're filling out this, we have 4 electrons, 1, 2, 3, 4. Now this combination over here is actually our HOMO, and that is what we're going to use for this particular diene. And this diene is quite impressive at some point, because in here we are including an electron donating group, and what that result is that we're going to have a particular shift in the electrons moving from this particular region to this particular region, where we're going to have a bigger node over here. So once you have you're going to have a bigger orbital coefficient over here compared to the other 3 over here, because in dienes, which are actually electron donating groups, the electrons is actually going to be much more donating to this particular region, which makes the coefficient to be much more bigger in this particular carbon over here. So therefore what we have in the particular result is we're going to have a molecular orbital which has a bigger node over here, but all these guys are quite small. We have our OH because we have our electron donating group over there. Now in terms of the in phase and out of phase, we need to replicate this particular part over here, where these first 2 over here are in phase. So I'm going to shade the bottom over here and shade the bottom over here as well. However, the top here will be shaded and this top here will be shaded, so that these 2 will be in phase and these 2 will be in phase, but these 2 over here are out of phase, and we are having our node over there. Now on the other side, we have this particular reagent over here, and it's quite interesting because we are having 2 substituents over here, and we have our pretty much a carboxyl groups over there with our 2 double bonds over there. Now the only thing different over here is that one of these particular double bonds over here will actually have a carbon that has a much more bigger coefficient in terms of its LUMO state. Now, before we're talking too much, we just need to look at only two ways of generating the particular combinations for the molecular orbitals of either of these two. One, we have a lower energy one with just both of them being in phase, and the last one is the other out of phase. So what that means is that we just have our LUMO which are out of phase with each other, and this LUMO will actually not have any electrons, and this LUMO will need electrons in this case. Now, for the need to have an electron, the electrons must be moving away from you. Now, there are possible ways of making electrons to be away from you coming from this structure. We either have this electron coming off in such a way that this carbon here is much more electron withdrawing, and then what that happens then is not electron withdrawing, electron empty, and then we have this actually pulled over to this oxygen over there. Or on the other side, we have this particular oxygen over here donating electrons towards this particular oxygen. Therefore, what that means is that these carbons over here will not have any change in their molecular orbitals, because electrons are actually donated to their molecular orbitals. But in here, we have this carbon where there's a lack of electrons over here because you are withdrawing it from this particular oxygen over there. So what we have here is that we're going to have our own state where we're going to replicate this, and now what we have here is a bigger node over here, and we're going to make this to be shaded, and I'm going to tell you the reason why. I'm going to make this to be shaded, and this part here will be quite smaller, and this bottom over here will be shaded in terms of the double bond. And in here we're going to have oxygen over there, and we're going to have an oxygen over there, and in here we're going to have our O-methyl group there. Now, something quite interesting we have over here. It doesn't matter the combination, you can either change this to be shaded, or this to be shaded, or make this to be shaded and make the bottom over here to be shaded. Now, in terms of the orientation or the positioning of these two molecules, one, you need to make your diene to be above the dienophile, and this dienophile, that is, if I can spell it correctly, the diene must be above the dienophile, and the positioning of this molecule should be cis with each other. Now, in terms of cis, let me give you a molecular model over here. Now, we have this particular model kit over here. We have our diene. Let me try to zoom this in. So we have our diene over here, and we have our double bonds over here. Now, these double bonds are perpendicular to the plane of this particular molecule. Now, what we have in this case is that we have our hydrogens, hydrogen, hydrogen, hydrogen over there, and the orbital nodes will be bigger, the biggest over here, big over here, big, big over here. Now, because we have our withdrawing group over there. Now, this will be at the top, and that will be our dienophile, where we're going to be focusing more on this particular reagent, which has the BNO over here. So this is the BNO over here, and over there we have our double bond that's going to be involved over here. Take note that this will be the bigger node that will be positioned here, sorry, the bigger molecular orbital over here, and in here we're going to have a really huge molecular orbital over here. Now, how are we going to position this particular molecule? Do we position this like this, or we position it the other way? We position it this way because there's a form of, if as the molecules are getting close together, there's a kind of an interaction within this particular pi system, and this particular pi system coming from these oxygens and also the carboxyl groups over here and the carbon with the electrons over here. So therefore there will be some kind of interaction, which is a dipole interaction. And then what happens next is that once this positioning is enhanced thermodynamically, it makes it to a much more stable and then be prone to orbital overlap. Now when you now exhibit the orbital overlap, this big node over here will interact with this big node, and what happens then is that the big nodes will interact and the the big nodes will interact and the small nodes will interact with each other, thereby forming sigma bonds over here and over there. And what that is that the hydrogens over here will be pointing away from me alongside the BNO, which is pointing away from me, and this hydrogen over here and over there will be pointing towards me. That is what we have in terms of the stereochemistry of our product. So that is just a molecular model of what we got over there. And now drawing this, once you're able to see that, once you draw this, what we get is our diene positioned here with a big node, and this is being shaded, and that all these cells are small. However, this part here is pointing upwards, is shaded, and down is not shaded, and we have our OH over there. And on the other side we have our that is actually pointing downwards. We have the dienophile with this particular compound over there in the cis formation, having a big node where this bottom over here is shaded, and we have this pointing downwards, and this other orbital is smaller, so that in such a way that the bottom over here is shaded, and we have that ME, and over here is our OBN. Yeah. Now what we got in this particular process is that we're going to have an overlap where this will overlap with that and this will overlap with that at the top, and then our cycloaddition will be electron donating to this, that coming to this carbon, and then this orbital is being reformed over there. So that's about it for this. To get this, thanks for watching. Please don't forget to hit the like button, share and subscribe. Bye.